So we've already, well, actually, no, we haven't really done these types of numbers yet, irrational numbers. Um, all the square roots and the cube roots we did in the previous lesson usually had a whole number or fraction in it. Like the cube root of 27 is 3. Okay? The square root of 1 over 100 is 1/10. Okay? Those answers were whole numbers or fractions or even decimals, but decimals that ended. Okay? We haven't talked about ones like square root of 3, which is not a whole number. Okay? It's 1 point something. And we don't know, I mean, we talked about last year how we kind of take a guess as to what it is between 1 and 2, maybe 1.8 or something like that. Cube root of 25 is not a whole number. It's going to be a decimal number. And these numbers actually turn out to never repeat and never end. Okay? So those numbers are called irrational numbers, which we'll get to in a second. Just before that, let's just review we did this last year. The natural numbers. We use a capital N to represent natural numbers, and then the counting numbers, starting at 1, 2, 3, etc. The whole numbers is the same as the natural numbers, except we add 0. And then we count up forever. And that's represented by W. The integers takes the natural and the whole numbers and adds negatives, but no fractions or decimals. And integers, we actually use the capital Z, because I stands for something else in math that you won't see until like university level. And the integers go in 2 directions forever. So basically we start at 0 and we can go up forever, 1, 2, 3, 4, etc. And we can go down forever, -1, -2, and down forever. We did a lot of work on these rational numbers. Last year, and we actually call these cube, because we use R for something else, which you'll see in a second. Okay? We can't write rational numbers in the notation like we did with the previous 3, because they're like, how do you count up and down? Rational numbers are fractions, all the numbers above here, decimals that repeat or end. So how do you list those? Like, where do you start? I mean, okay, you can start at 0 in the middle, but what's the next rational number after 0? A really, really small number, like 1 over 1 and infinite zeros. So you can't really write using notation. So a rational number is any number that can be written as a fraction. With one exception, the denominator cannot equal 0, because we can't divide by 0. So your examples would be all the numbers above. So examples would be natural and whole numbers, because they can all be written as fractions. Integers, because they can always be written as fractions. Any of the above numbers can be written as fractions by tossing it over 1. So 2 as a fraction is 2 over 1. Negative 10 as a fraction is negative 10 over 1. So all the above numbers are also rational numbers. But we also include any fractions. And decimals that end or repeat. So fractions obviously can be written as fractions. But decimals, like if you think of 0.5, it ends after 5. That can be written as the fraction 0.5, 1/2. Okay. What about 0.3 repeating? That's a decimal that repeats. How would you write that as a fraction? 0.3 repeating. What's that? As a fraction. Really? Yes, 1/3. There's no lines. There's only a line in the decimal portion. 0.3 with a line over it is equal to the fraction 1/3. Yes. Right? So if rational numbers can be written as fractions, what do you think irrational numbers are? That's cube bar. What do you think they are? If rational can be written as fractions, irrational can't be. Can't be written as fractions. So really what you're thinking of are decimals that never end or never repeat. You should be able to think of a number that never repeats or never ends. You've used it before. Pi. Some people write it as 22/7, but that's only approximate. That's not exactly pi. Okay? Square roots of non-perfect squares. So if you think the square root of 0 is 0, square root of 1 is 1. The square root of, and those are rational numbers because you can write them as fractions. The square root of 2 is 1 point something, and it turns out that decimal never repeats or it never ends. Same with the square root of 3. Square root of 4 becomes 2. That's rational. The square root of 5 is not, square root of 6 is not, etc. Same thing because we talked about cube roots of non-perfect cubes. So like the cube root of 0 is 0, the cube root of 1 is 1, the cube root of 2 is 1 point something. Turns out it's a decimal that never ends or never repeats. Same with cube root 2, 3, 4, 5, 6, 7. What about cube root 8? Rational or irrational? Cube root of 8. Rational. because it's 2, which can be written as 2 over 1. Okay. And you can show these using a diagram, and we used this diagram last year. All of those previous numbers, natural numbers, whole numbers, integers, rational numbers, irrationals, are called, all of those together are called real numbers. And that's where we use R. So all previous number systems that we did on the first page. So imagine we have a huge rectangle that contains all those real numbers. And within all the real numbers, there's different number systems. Counting numbers or natural numbers, whole numbers, integers, rationals, or irrationals. So let me ask you a few questions from the previous page. Is every whole number a natural number? Yes or no? Is every whole number a natural number?
No, there's 0.
Right. Is every natural number a whole number? Is every natural number part of the whole numbers? Yes. Is every whole number part of the integers? No. Here's all the whole numbers. Aren't they also part of the integers? Is every integer a rational number? Yes. Okay. So imagine if we look at it graphically, we can put the natural numbers in here. Because every natural number in here is part of the whole numbers, which is a bigger circle around it, but only actually includes 0. All the whole numbers are integers. Whoops. And all of these can be written as fractions. If you can't write it as a fraction, it's outside the Q oval, but it's still in the rectangle. So all the irrationals, the ones that you can't write as fractions, are there. Now we did this last year with a few numbers. Where would I put the number -5? Natural? No, it's a whole number? No, integer, right? So -5 will go here. Where would I put the number 2/3? Okay, so inside,
Here.
but outside, oh, it has to be in here, right? I don't know why I put that there. My mistake. Feel free to correct me. Where's 20? Whole number? And you can go in further inside, right? It's a counting number. What about 0? Inside the W. What about pi? Outside. Outside. Irrational. You want to give me the letters?
2, 1.
Inside or outside?
No.
Oh,
Wait.
yes, you're right.
Yeah.
Yeah.
I'm not.
Yeah. Uh, Square root 16. All the way in here. Because it can be written as 4. 6.7 repeating. What's that? Irrational? You just throwing things out there? Oh, integer. Natural. It's one of those. Irrational? So you can't write 6.7 repeating as a fraction. Good. Hold on. No, I'm going to stick with it. Square root of 17. Sorry? Irrational. Cube root 9. Sorry? Natural? Cube root 9. Who said irrational? Irrational is correct. You can't take it exactly. It's going to be a decimal, which means it's going to be irrational. Cube root of 8. Natural. Because it's exactly 2, which is a counting number, so it can go all the way inside the end. Okay, so we sort of getting the idea here. Okay, let's just look at a couple more examples. One. So let's just look at these three, say whether they're rational or irrational, and then just tell me why. A. Why? Because it's a yes. Rational. Correct. This one. Root 14. Irrational. And really the explanation we could say is non-perfect square. Which means it's going to give us a decimal that never ends or never repeats. And finally, rational. Why?
Because
Because, yeah. Okay, what is it? Yes. And how do you write 3 as a fraction? Yeah. Rational because it's exactly 3 or 3 over 1. So it can be written as a fraction. Okay. And the last example, and we're going to do this without a calculator. You can do it. So we're going to take these 4 numbers. Could be rational, could be irrational. They're all square roots and cube roots. And order them from least to greatest. So think about it. Why don't we, like, what do you think the smallest one's going to be? Any idea? And why? There's one that should stand out as the smallest. This is going to be negative something. Because remember, when you take the cube root of a negative, the answer is negative. So like the cube root of -1 is -1. The cube root of -8 is -2. So this is going to be negative, and it's the only one. So that's got to be the smallest when we start our list. The other three are going to be positive, but now we got to order them. Well, can you tell me any of them exactly? That's 3. What's the square root of 18? Well, it's an irrational number because I can't take it exactly, but it would be approximately what? Square root of 18. Can you think of a perfect square near 18? 16. What's the square root of 16? What's the square root of 18? Well, probably a little smaller, but 4 point something. 4 point, and I know this isn't like really nappy looking, but 4 point something. So I know that this is smaller than this. Now, what about this one? Cube root of 13. Can you think of a perfect cube near 13? You should know 8. What's the cube root of 8? What's the cube root of 13? 2 point something. We don't have to be precise because now it's obvious what the order is. This is the next smallest, cube root 13. Square root 9 is the next one, and the largest is going to be square root 18. So that's how you can sort of use estimation to figure it out. Okay? So all I want you to get from this is just an idea of what irrational numbers are. Okay? We can find them, but we can't find them precisely. Like we know the square root of 3 is 1 point something, but we can't write it exactly because it never repeats or never changes. Okay? Okay.